We looked in the last video about symmetry for functions. This time what we're going to do is we're going to take a look at symmetry with respect to relations. And it's actually going to be pretty easy to determine this because the test is very similar to what we did before, except we're going to be plugging in for both x and y for negatives. So what we're going to do is, first of all, we're going to have three types of symmetry for relations, but not for functions, okay? So what we could do is we could determine if a function or, I'm sorry, if a relation is symmetric to the y-axis. Then what we're going to do is we're going to plug in negative x, and what's going to happen is we're going to get the exact same equation. All right, so actually what that means is going to be the same test for even functions. All right, so that's good. But if we're looking at symmetry with respect to the x-axis, and that's not going to be a function, a relation, but what we're going to do is we're going to substitute negative y in. And if we get the exact same thing that we started with, that means that it's going to be symmetric about the x-axis. And then finally, if we want to determine if a function is going to be symmetric about the origin, for a relation, okay, not for every function, we're going to plug in both negative x and negative y, all right? And that should give us the exact same thing that we started with. So, and by the way, there are functions that exhibit multiple symmetries. So just because we get one positive test for symmetry, that doesn't mean we stop, all right? That means that we should probably keep going and test all three of them. So when I'm asking you to do this, you should test for all three of these, all right? And that's what we're going to do in each of these examples. So we have this relation y equals x to the fourth plus x squared. And so let's first of all test for symmetry about the y-axis. And to test for symmetry about the y-axis, we're going to plug in negative x. So y is going to be equal to negative x to the fourth plus negative x squared. And again, what that means is that when we raise anything to an even power, a negative number, it's going to go back positive. So this becomes y equals x to the fourth plus x squared. And that's the same. And so that implies that there is symmetry about the y-axis. All right. But that means that doesn't mean we stop. So now we're going to test for symmetry about the x-axis. And to test for symmetry about the x-axis, we're going to plug in negative y. And so if we do so, we get negative y equals x to the fourth plus x squared. And there's nothing that we can do to simplify negative y because there's nothing being operated on, okay? So it is not the same, which implies that it is not symmetric about our x-axis. And then finally, let's see if there's symmetry about the origin by plugging in both negative x and negative y. Okay, so for our origin, we're going to substitute negative x and negative y. And so if we do so, we get negative y equals negative x to the fourth plus negative x squared. And if we simplify the right-hand side, well, that's easy. We just get negative y is equal to x to the fourth plus x squared, all right? But that's the exact same expression that we just got before we checked for symmetry about the x-axis. So since, again, it is not the same, that means that there is not symmetry about the origin. All right. And so the only symmetry exhibited is about the y-axis for this function. And of course, if we wanted to, we could graph it. And I know the problem says don't graph it, but let's just graph it just to see what happens. And we can see that it's got this sort of curved shape to it. And it does have symmetry. So you can see right here at this point, it's the same here and here about the y-axis. So a secondary example, we have this x cubed plus y squared equals 2. So to see if there's symmetry about the y-axis, remember we plug in negative x. That's going to be negative x cubed plus y squared equals 2. Now simplifying this, remember if it's to an odd power, that means that we're not going to change the sign. It's going to stay where it is. Okay, so at this point, what we're going to say is that there is not symmetry. Okay, so it's not the same, which implies it is not symmetric about our y-axis. All right, but let's try the x-axis and the origin. So for our x-axis, remember we plug in negative y. And so that's going to be x cubed plus negative y squared equals 2. If we square a negative y, that just becomes a positive y. So that's going to become positive y squared equals 2. And I want you to notice that that is exactly the same as what we started with. Okay, and that's the goal. If we get the exact same thing, so it's the same, which implies that there is symmetry about the x-axis, right? And when I'm done with this, we'll graph it just to see what happens with this, okay, to verify that. Okay, so that's good. We got one positive test. And then finally, let's check the origin. All right, so for the origin, remember you plug in negative x and negative y. And so this becomes negative x cubed plus negative y squared equals 2. The x cubed is going to keep its sign because it's an odd power. The y is going to go back to positive because it's an even power. And notice that, again, this is not the same. In fact, we get the same result as the y-axis for test. And so that means they're not the same. And so that means there is no symmetry about the origin. All right, and so what that means is that we just go through and say that there's only symmetry about the x-axis. If we graph this relation, all right, so we're going to say x cubed plus y squared equals 2, right? And we can see that this point and this point are exactly the same, all right? And then we can see that this point and this point are the same when we reflect them about the x-axis. And so this point and this point, all right? And so it just shows you that it does have that symmetry. So we can do this by hand without utilizing any without using any sort of computer algebra system or grapher, but we certainly want to check. All right, so the only test that comes up positive is symmetry about the x-axis. Right now, one final example of this is we have this x to the fourth minus 2 equals y to the sixth, and if we substitute, so let's start by testing for symmetry about the y-axis as we have in the previous two examples. And so remember, that's plugging in negative x, so we get negative x to the fourth minus 2 equals y to the sixth. And that's the same as positive x to the fourth, because we have an even power, minus 2 equals y to the sixth. So we certainly see that it does have symmetry about the y-axis, because we have the same expression that we started with. So notice that's the same. But let's check it out for the x-axis. So for the x-axis, we just plug in negative y and into our relation. So we have x to the fourth minus 2 minus y to the sixth. We have an even power, which is 6. So that means it's going to turn it back positive. So we have x to the fourth minus 2 equals y to the sixth, noticing that that is exactly the same as what we started with. So indeed, we have symmetry about the x-axis as well. So there's two symmetries going on at least, but we haven't checked for the origin. And so when we test for the origin, we plug in negative x and negative y, okay, back in. And so if we do so, this time it should turn out to be symmetric about the origin as well. So we have negative x to the fourth minus 2 equals negative y to the sixth. And again, we have even powers, so that means that it's going to turn positive. And so it's the same. And so we have symmetry about the origin. So it actually has three different symmetries to it. So it's symmetric about the y-axis, about the x-axis, and about the origin. Now we can graph this, and in fact we will. So we have x to the fourth minus 2 equals y to the 6th. All right. And this is what we get out of this. And if you pick any sort of point here, so pick this point here, or I'm sorry, over here, so reflecting the y-axis. So we have the same distance from here to here. It looks like it falls at 1, all right? And then also about the x-axis, it looks like that this point is equidistant vertically from the x-axis. But in the origin, if we go over to like here and we reflect at catty corner, it has the symmetry about here and here, but also here and here if we go diagonally. All right, so certainly the graph verifies that the symmetries are reflexive of what we suggested, all three of them. So that's how we can determine symmetry of relations. So we've seen how to determine symmetry algebraically of functions, and then how to determine symmetry algebraically for relations. So in the next video, we're going to take a look at a few more examples of some of the stuff with respect to maxima, minima, with respect to graphs.